Hello, Mr. Courtney here. In this video, we're talking about mole concept, and we're going to be specifically looking at empirical and molecular formula of a compound. So we'll be looking at how to calculate empirical formula, how to calculate the molecular formula, and how to get the molecular formula of a hydrate. So we've used the formula for compound to calculate percent composition. In this lesson, we're going to see how we can use the percent composition to determine the formula of a compound. So what is the empirical formula? The empirical formula is the smallest whole number ratio of the elements in a compound. When we say the smallest whole number ratio, we mean the simplest form that the compound can be broken down into. So when we look at the ratio of the elements, so in this element we have 1 carbon, 2 oxygens. We cannot break it down into any simpler form, so that is our empirical formula. In H2O, we cannot break it down into a simpler whole number ratio, so that's our empirical formula. But when we look at C4H10, we see that it is able to be broken down into a simpler formula. It is not the simplest whole number ratio. We can divide the ratio of carbon to hydrogen by 2, and we get a simpler ratio of C2H5. So C2H5 is the empirical formula for C4H10. So how do we calculate the empirical formula? First, we need to know the mass. And then we convert our mass into moles. And how do we do that? By dividing by the atomic mass of each element. Now, if you're given percent composition, we're going to assume it's 100 grams of the compound. Why can we assume it's 100 grams of the compound? We can do that because a percent is out of 100. So if you're told the percentage of something is 25%, that means out of 100 grams, you have 25 grams of that element in the compound. Next, we need to determine our mole ratio. So what is the mole ratio of each element in the compound? What we're going to do is look for the element that provides the lowest or the smallest number of moles and divide all the number of moles by that element, that number of moles. And that will give us a whole number. Now, if we do not get a whole number, we need to multiply the ratio by some number, some factor that will give us a whole number. Once we've done that, we're going to use the ratios as the subscripts in the formula. So let's look at an example. So a compound is made up of 79.8% carbon and 20.2% hydrogen. And we're asked to find its empirical formula. So first thing, list your elements present in the compound. Then we determine what mass we have. Now the mass of carbon in the compound is 79.8 because we convert percent to grams, and the mass of hydrogen will be 20.2. We divide now by our atomic mass of these elements to get our number of moles. So for carbon, we divide by 12.0, that gives us 6.65. For hydrogen, we divide by 1.01, that gives us 20.0. Now after we have moles, if you refer back to your steps, we need to get mole ratio. So we look at the number of moles we have for carbon and hydrogen. We see that carbon has the lowest number of moles, which is 6.65. So we're going to divide each number of moles, that is 6.65 for carbon and 20.0 for hydrogen, by 6.65. That gives us a mole ratio of 1 for carbon and a mole ratio of 3 for hydrogen. So our empirical formula tells us we have 1 carbon and 3 hydrogen. So our empirical formula will be CH3. In the second example, we have an oxide of aluminum which is formed by the complete reaction of 4.151 grams of aluminum with 3.692 grams of oxygen. And we're asked to calculate the empirical formula of this compound. So we're given grams, we're not working with percentage, so we're given a specific amount of grams of each element. Aluminum and oxygen. Again, we list our moles, our mass, sorry. Now we get our moles by dividing by the atomic masses of these elements. So for aluminum, we'll divide by 27.0. For oxygen, we'll divide by 16.0. So we look at our number of moles for each element, and we use that to determine our mole ratio. In this one, we see that aluminum provides the smallest number of moles. So we'll divide the number of moles of aluminum and oxygen by each one by 0.1537. We get 1 mole for aluminum and 1.5 moles for oxygen. Now, we didn't get a whole number. And if you go back to the steps, we said if you don't get a whole number, you need to multiply it by some factor that will give us a whole number. So we're going to multiply the 1.5 and the 1, multiply both of them by 2. So that gives us 2 aluminums and 3 oxygens. So the empirical formula for this compound is Al2O3. So what this is showing us is basically how we move from mass of the elements to empirical formula. So we start with mass percent of elements. Then we go, if we given mass percent, we assume it's out of 100 grams. Then we get grams of each element. Use the atomic weight, so we divide by atomic weights to give us moles of each element. So that gives us moles. Then we calculate our mole ratio by dividing by the smallest amount of moles. And then we can use those numbers to give us our subscripts in our compound. And that gives us the empirical formula. So molecular formula. Molecular formula is the actual number of each element, or the actual amount of each element in the compound. So that's what it tells us. It gives us a ratio of the elements in the compound. Not the simplest whole number, but just a ratio. So it could be C2H4. It is not the simplest form, but it is the correct ratio of the elements in the compound. The empirical formula and the molecular formula can be the same. Let's look at some examples. In water, H2 is the empirical formula and the molecular formula because it is the actual ratio of the elements in the compound, and it also represents the lowest whole number ratio of the elements in the compound. For hydrogen peroxide, H2O2 is the molecular formula, but it is not the empirical formula because it is not the simplest whole number ratio of the elements. The empirical formula will be HO. So calculating molecular formula. To calculate molecular formula, we need to know the ratio of the molecular mass to the ratio of the empirical mass. We say molecular formula mass, empirical formula mass. So we need to know these two values. So to get N, that is how many times is the molecular formula larger than our empirical formula. We take the molecular mass and divide it by the empirical mass. Once we get that ratio N, we're going to take that and multiply it by the empirical formula to get our molecular formula. When we get that, we're going to multiply each subscript in the empirical formula by N. So that's very important. We're going to multiply each subscript by the empirical formula by that ratio N. So let's look at an example here. We're told a white powder is analyzed and found to have the empirical formula P2O5. The compound has a molar mass of 283.9 grams, and we need to find the molecular formula. So first we need to determine the ratio. How many times is our molecular formula greater than our empirical formula? So we need to find the empirical mass of P2O5. Once you do that, you get the empirical mass to be 142.0. So now we're going to divide our molar mass. So we take our molar mass and divide by, this is our molar mass here, and divide by our empirical mass. That gives us 2. So now we have 2 as the ratio. We multiply our empirical formula by that ratio to give us our molecular formula. So P2O5 times 2, and remember, we're going to multiply the subscript. So 2 times 2 and 2 times 5. So that gives us P4O10, and that is our molecular formula. Now, a compound used as an additive for gasoline to help prevent engine knock shows the following percent composition. So we have 24.7% carbon, 4.07% hydrogen, 71.65% chlorine. We're told the molar mass is known to be 98.96. And we're asked to determine the empirical formula and the molecular formula of this compound. So we're incorporating both steps in this problem. So we start by calculating our empirical formula. So we have carbon, hydrogen, and chlorine. And since we're given percent, we're going to assume it's out of 100 grams. So the masses will be the same as the percentage, except we change it to grams now. Then we divide by the atomic masses of each of these elements to get our number of moles. So we divide by 12.0 to give us 2.02 for carbon, divide by 1.01 for hydrogen, and that gives us 4.03. Divide by 35.5 for chlorine, that gives us 2.02. We now need to know our mole ratio. So we look for the smallest number of moles that we calculated before. We calculated 2.02, 4.03, and 2.02. So 2.02 is the lowest number of moles, or the smallest number of moles. So we divide the number of moles we calculated for each element by 2.02. So we get 1 for carbon, 2.0 for hydrogen, and 1 for chlorine. So that means our empirical formula is CH2Cl. Now we need to find our empirical mass, or the empirical formula mass. We find that to be 49.5 grams. Once we found our empirical formula mass, now we need to find the ratio of the empirical mass to, of the formula mass to empirical mass. So we divide the formula mass by the empirical mass. And then we're already given the molar mass, or the formula mass, which is 98.96. So we take our 98.96 and divide it by 49.5. And that gives us approximately 2. So that means our molecular formula, is 2 times larger than our empirical formula. So we multiply our empirical formula by 2. So that'll give us C2H4Cl2. Because again, we're multiplying our subscripts. So we multiply our subscripts. So 2 times 1, it gives us a 2. 2 times 2 is 4. 2 times 1 is 2. A hydrate. A hydrate is a compound that has water molecules chemically bonded to it. So any compound that has water molecules chemically bonded to it is considered a hydrate. How do we know if something is a hydrate? Here we have a compound, a salt, followed by a dot, and then certain amount of water molecules attached to it. This number tells us how many water molecules, and this H2O, the water molecules attached to it, is what lets us know that this is a hydrate. You can also look at the name of the compound. The name of the compound will contain the term hydrate. So we have copper 2 sulfate tetrahydrate, and tetra tells us we have 4 water molecules in it. Now, to name the hydrate, the name of the salt, we name the salt and then we follow it with the term hydrate and with some numerical prefix attached to it. The numerical prefix tells us how many hydrates we have in the compound. So for this one, if we were to name this compound, we name the salt first, sodium carbonate. So we have sodium carbonate, then we have water. And how many water molecules do we have? We have 10. So that's sodium carbonate. And since we have hydrate, we know it has water molecules in the end with the term hydrate, and we have 10 of them, it's decahydrate. So the name of the compound is sodium carbonate decahydrate. So what's the formula for copper 2 sulfate tetrahydrate? So copper 2 sulfate, so copper is plus 2, sulfate is minus 2. So that's CuSO4. We put a dot, and tetrahydrate will be 4H2O. Now the formula mass, we do the formula mass just as how we've done for any compound before, just by adding the individual masses up together. So we do for copper, sulfur, oxygen. Now we can do water as 18.015 or 18.02 multiplied by 4, or if you want to do each one individually, 2 times 1.01 plus 16 and all that multiplied by 4, which is the same thing, and that gives us 231.5 grams per mole. To determine the formula for hydrate, now the moles of water present is going to be a whole number multiple of the moles of salt present, and we saw that before. We had one mole of the salt and 4 moles of the water in copper 2 sulfate tetrahydrate. So let's see how we determine that. We're going to work it out simple. Similar to how we did empirical formula, except we're not going to be using elements, we're going to be using the compounds, whatever the salt is and the water molecule. So we look at this problem. We're given a sample of a hydrate, which is 10.407 grams, and is heated to drive off the water. The anhydrous, this is important, the anhydrous or the dry sample has a mass of 9.520 grams. We want the formula of the hydrate and then the name of the hydrate. So first of all, we know we have barium iodide, that's our salt, and we have water because it's a hydrate. We need to know the mass of the hydrate, of water, sorry, and the mass of barium iodide. Now, since we're told in the beginning, the sample is the hydrate, then we dried it off. So the mass of the dry sample will be the mass of the salt. And the difference between the two masses will be the mass of water. Then we calculate moles. We divide 9.520 by the formula mass of barium iodide. That gives us the number of moles. We do the same thing for water. Divide by 18.02. That gives us number of moles. And again, we're going to calculate our mole ratio. This here is the smallest number of moles. So we're going to divide this by itself. And we're going to divide this by 0.02434 also. When we do that, we get 1 for barium iodide and 2 for water. So that tells us in every mole of the hydrate, there's 1 barium iodide and 2 water molecules. So Bai2.2H2O. So that's barium iodide dihydrate because we have 2 water molecules attached. So we're going to talk about combustion analysis. In combustion analysis, it's used in organic and analytical chemistry to determine the empirical formula of a pure organic compound. And as you can see here, the sample is passed through a furnace. Then you're going to have an absorber, something that absorbs the water molecules, and then something that absorbs our carbon dioxide. Oxygen and other gases will be given out at the end. So once the substance is combusted, the products, and usually is going to be carbon dioxide, water, and oxygen gas, can be analyzed to determine the empirical formula. So we get mass, we go to moles, and then we do empirical formula. So let's look at an example. So in the complete combustion of a sample of propane gas, we ended up with 2.641 grams of carbon dioxide and 1.142 grams of water as the only products. Find the empirical formula of propane. So we know propane is going to contain carbon and hydrogen. So that means from carbon dioxide, we need to find out the moles of carbon, and from water, we need to find out the moles of hydrogen. So we start with this. We start with 2.461 grams of carbon dioxide. We know in 1 mole of carbon dioxide, we have 44.0 grams. So that gives us moles. Now look at the formula for carbon dioxide, CO2. We have 1 carbon atom in 1 mole of carbon dioxide, or 1 mole of carbon atoms in 1 mole of carbon dioxide. So that gives us 0.0600 moles of carbon. For water, we start with 1.442 grams. In 1 mole of water, we have 18.02 grams, the formula mass. And in 1 mole of water, we have 2 moles of hydrogen because we have H2O. So here we have 2 moles of hydrogen. That gives us 0.016. Same thing as we did before, we're going to calculate our mole ratio. This here, we have the smallest number of moles from carbon. So we do our ratio of carbon to hydrogen. And that gives us 0.06 divided by 0.06 for carbon, 0.16 divided by 0.06 for hydrogen. That gives us a ratio of 1 to 2.67. So now we don't have a whole number for our mole ratio, and we need whole numbers. So we're going to multiply everything by 3. So that gives us 3 carbon atoms, 8 hydrogen atoms. So that means our empirical formula is C3H8. Let's look at one more. Now, suppose you were able to isolate an acid from clover leaves and know that it contains only the elements carbon, hydrogen, and oxygen. When you heat it, when you heat 0.513 grams of the acid, we get 0.501 grams carbon dioxide and 0.103 grams water. We need to know the empirical formula and the molecular formula. You're also told that the molar mass was determined to be 90.04 grams per mole. Now notice we're given that it's made the compound is made up of the elements carbon, hydrogen, and oxygen. But we're only given the mass of carbon dioxide and the mass of water produced. So from carbon dioxide we can determine grams of carbon, and from water we can determine grams of hydrogen. Then we can find the grams of oxygen as being the remainder. Subtract those values from 0.513 to give us grams of oxygen. So we do it similar to what we did the first time in the previous example. So 0.501 grams of carbon in 1 mole of carbon dioxide, and in 1 mole of carbon dioxide we have 44.01 grams. We know that we have 1 mole of carbon dioxide, 1 mole of carbon in 1 mole of carbon dioxide. Then we're going to convert our moles to grams. So we have 12.01 grams of carbon in 1 mole of carbon. So in the compound we have 0.137 grams of carbon. We do the same thing for water, 0.103 grams. In 1 mole of water we have 18.02 grams. Then we look at the mole ratio. In hydrogen, in water molecules, we have 2 moles of hydrogen in every mole of water. Then we multiply by 1.01 grams in each mole of hydrogen. And that gives us 0.0116 grams. Once we've done that, we can calculate the mass of oxygen by subtracting these two values from 0.513. So now that we have the mass of each element in the compound, we can go ahead and calculate empirical formula. So we start with our elements. We start with the mass, which we just calculated. We already know the moles of carbon and hydrogen, because we could have determined that already. So we divide by the atomic masses to give us the moles. We do the same thing for oxygen. Now we look at the values that produces the smallest number of moles. So let's go with this one. These two are approximately the same. Okay, so we go here. So for mole ratio of carbon, we get 1. Hydrogen, we get 1. Oxygen, we get 1.98. So that tells us it's approximately 1 to 1 to 2. So empirical formula is CHO2. But we still need to find our molecular formula. So to find molecular formula from empirical formula, we must know our empirical formula mass, or the empirical mass. And that's 45.0. And we were given the molecular formula of the compound previously in the question. So we have 90.04 grams per mole as a molecular formula. We divided by our empirical formula mass. Our molecular mass is 90.04. We divided by the empirical mass of 40.0. That gives us a ratio of 2. Once we have the ratio of 2, we're going to multiply this by our empirical formula, which is CHO2, to give us our molecular formula. So that will give us C2H2O4. Okay, so that takes us to the end of this. Until the next time, I'm out. Blessings.